Homework for, let's see. So yeah, this for this part A of this, I guess I wanted you to say, I guess I wanted you to show the plot of the correlation function and say like why. I mean, some of you did okay on that. I think most people. Like it should be should go to 1 at the high end, and it should be 0. So that's like the average density. Oops. It's kind of a hardcore, and then there's like what's left over. You get a peak and a dip, and the peaks is like kind of nearest neighbor, and then the next thing is a void here. And then like the next, then those also, this nearest neighbor also excludes the next one. The 2. So there's another, this is the excluded volume. And this is like the second like void, whatever. There's a space left, and then the second nearest neighbors, and then go like that until you reach it. When you get far enough out, it's just the average density that you see. So anyway, so you take that G bar and subtract 1, you just get kind of this, you set the 0 to here. And then you have like, this is really literally what I wanted you to say is like, then you end up with this is like the potential, like if you average that out, that ends up being like the integral of that thing's going to be like the potential, the extra potential that's left, like the energy that's of exclusion for the things. So that's kind of the logic behind why that's, without the logic, if you just say it isn't really good enough, like you have to say somehow like why a correlation function would have something to do with, maybe you didn't need to, making the plot as easy as for me, but if you have to kind of say why, not just say like it is, you know what I mean? Like binary, how does this approach different? Let's see. Explain why a binary correlation function is described. So why is it that you can take that and then get like thermodynamic parameters from it? You know? Not the equations. In other words, if you sum up all the G11, G12, G22, then you can get the excluded volume. That's true. You know, and it's kind of in that plot too, that would show that it basically somehow you have to make an argument for why that's related to thermodynamics. I hope you can kind of see that. In other words, just given the function or just saying that it is. In other words, a lot of the answers were like just repeat the question back. We'll see this over and over again. So I'm trying to get you to think the way I think, the way I'm looking at it, you know, and I think it's, to me, it's the right way, you know, but basically there's several ways you can answer that question. You could just say it is, like it is a function. So you just give the question back. So you say the correlation function or the integral of the correlation function gives the thermodynamic parameters. It's just like restating the question. It's not an answer to it, right? And then you could say, what else do people say? I don't know, any kind of logic that would link together like why it is true, you know, that you could have a correlation function like a structural feature, an organizational feature, and then that what is the link between that and thermodynamics? There's kind of different ways you could do it. One way is through that plot, you know, and do the integral of the plot and show that. When I'm asking a question, I want you to say, can you guys see what I'm talking about? Like to say exactly what the reasoning is behind it. In your opinion, it doesn't have to be copied from somewhere. It's like what, like you've looked at it. So you could, I mean, it would be better to say, I don't think there's any relationship between the correlation of things and the thermodynamics at all. It doesn't, that's not true. Like that would be a better answer than saying this book said like that equals that, so that's the answer. Right? Because at least when you say it isn't, then I have to say it is and explain why it is. Right? But if you just say this book said it was, that's leaving you nowhere except to just parrot whatever someone else said and not, there's no thought behind it. So I'm trying to get you the answers I'm really looking for are like that you're thinking about it. Like, look at this thing, this is what I think about it. My opinion, it's like what I believe from this, so anyway, I hope that's kind of, so I took points off here, but and then people messed up the Monte Carlo thing. And they gave the answer for Monte Carlo for the molecular dynamics back and forth, A was really the big problem in this homework. Everyone did okay, but basically A was the problem. So I'll talk about Monte Carlo later on. Like I'll go through simulation stuff at like the second to the last chapter or something. So we'll go through these things in a little bit more detail. But Monte Carlo, what you should be thinking about is this icing model, like a grid with magnetization and arrows pointing. You got to flip one arrow and you're going to get the energy of the entire system. Could be millions of arrows. You're going to calculate the energy of the entire system. The energy dropped, that's good, I accept it. The energy went up. I'm kind of flipping a coin with temperature as the weighted coin. Temperature weights the coin if I'm going to take it or not. And sometimes you take the bad thing and sometimes you exclude it. And then basically it's going to march on changing the system point by point and then summing the energy every time. And so finally the system will evolve into an equilibrium, kind of an equilibrium lowest energy state by going through that process. So you have the energy right off because the energy is calculated every step. And then the molecular dynamics is basically Newton's laws. Things are bouncing around and they hit each other. There's repulsive interaction, 612 potential between the particles. It's like a bunch of pool balls bouncing around with certain functions that guide the interactions between the pool balls. So they're different approaches to how you'd simulate something. But if you do the pool ball thing, you don't have the free energy. So you basically need a way to calculate it, and that's what this Kirkwood off theory will do for you through the integral correlation function. But you have to kind of understand what a correlation function is, and then what it has to do with thermodynamics. Like you have to have a gut feeling to say what it has to do with thermodynamics, not spitting out just the answer of it. In order to get a feel for, like, in order to read the paper, like you have to have that, right? And you have to have that understanding a little bit. Rest of this, some people mixed up the Hildebrandt with the Flory-Huggins, so there's various ways you could mess that up. Basically, everyone got it right, Drive equation 9, so that got kind of confusing. It says derive equation 9, it said you should drive equation 10, but driving equation 9 is just the, it's from like the third slide in the solution stuff, we went through it. Solutions like this, that derives equation 9. Like you do the pressure, dg would be VVP, and volume for an ideal gas gives that thing, and then you end up with this, and that thing's activity. That's it. Like this thing, and then that's the activity that gives you whatever this equation 9 is. This thing. I mean, the activity is gamma x. And then I kind of said you could do this. So I gave 3 points if you did that, like derive this equation from that equation, just some derivatives. I should have given 3 points. I guess I missed it on one, but so I'll fix that. Anyway, everyone did okay on that business. Then explain the parts, everyone could explain that, and explain 22, everyone could do that, basically everyone. Like one person messed up E. One person, right, one person like looked back and then got the wrong paper. Anyway, E got messed up for one person. It was like almost comical because it was like in the other, one of the papers we did, and it was like, I forget what it was. Had to do with, or it had to do with something totally different, but there was an S in it. So they did that one, so it was just somehow messed up. The one we're looking for is orientation function. That the reason I mentioned is because we'll see it again. Like we'll see that function again, maybe over and over again. Anytime you have things with orientation, you want to describe them, you reach for that function. And it's 1 is perfectly oriented, 0 is random. If it's oriented the opposite of what you think it should be, it's -0.5. If it's perfectly oriented the wrong way, it's -0.5. He says he's got a 0.11 orientation. So that's like pretty low. That's almost like random. That's kind of like close to a random system. Like 0 would be random, 0.11 is pretty low. So anyway, so that Herman's orientation function, it turns out it's a Legendre polynomial. It's a second order Legendre polynomial. I think they're in even orders, like second, third, second, fourth, sixth, whatever. So it describes, it's just a weighting factor for orientation. Like, in other words, if you want to say what percent is oriented, it'll be this number. So here it's like 11% is oriented. So anyway, any questions on that homework? Everyone's doing okay. One person's got a B. Everyone says an A, like average. Look at the average grades. So everyone's doing okay in here. And I'm just going to give a solid, like if you get a 90, it's an A. There's no plus minus thing. The same with the B. If you get below a 90, it's a B. That seems to work out okay for me. Anyway. So there's no comments or anything on that. So I go, we get some stuff to finish in solutions. Then I go to this week's, the homework's on phase diagram. So I should be able to get through most of this stuff. I think it was 20, down what this was, I didn't bring the paper. I think it was 22. Maybe it was 24. Regular solution. Maybe it was 34. Let's see. So I went through this last time, but this will be a plot of the free energy. This is a plot of this equation, right? So here's our friendly entropy expression. They should be warm and fuzzy about, and this is adding in the non-ideal enthalpic interaction. And as you march through, so if you divide G by T, right, then this thing doesn't have a T in it, and this guy's like 1/T. So you can think about as you get to higher temperature, this term drops out and then you just have mixing. So at a high temperature, it mixes. When you cool it down, this is divided by T. This term will be smaller than that term. And then this term becomes larger at low T. So you divide it by a small number, and this becomes larger. So that leads to demixing at low temperature. Right. And if you plot this thing as a function of composition, as you lower the temperature, you go through this scheme. So when you're at a high temperature, T1, so T1 over here is T versus composition. You have a single phase, so it's a smiley face. Then as you cool it down, then the Hildebrandt term, interaction term, and the entropy term match each other at some point. You get this critical point where it's flat. And if you continue down into the two-phase region, the free energy has this kind of double lobe feature to it. Right? And the derivative of this versus moles would be the chemical potential. So if you draw a line here, these two things have the same chemical potential. They're in equilibrium, right? And that defines a phase diagram. So as you go to lower and lower temperature, so this is going higher, but it's a lower temperature. So the free energy is increasing as you decrease the temperature in this equation, right, in this guy. So basically, this is strictly just plotting that equation, right? And you get this kind of thing coming out. So this is the critical point, T3. T2 would be critical point, it's flat. And then T3, it starts to form the two lobes. You have that composition. And you map out this two-phase region. And the phases that are at equilibrium are like this composition and that composition. So if you're in this single phase, and then you cool down, you reach T5, say you're over here, well, you're gonna make a lot of this one because you're to the left, you're gonna make a lot of that equilibrium phase and not much of that phase. There's a tie line. So you have a point here, the distance, that distance decides how much that is, and that distance decides how much material is in that one. It's basically, if you take the whole distance of that line, divide it by from here to the composition where you are, divide that by the total distance of the line, that gives you the fraction of the phase of this phase. In other words, this would be the majority phase, and these would be domains within it. So you can start drawing out from a phase diagram, because you can draw out like what it would look like in a micrograph. Right? In other words, I start here, I go down there, then I'm going to get majority of this phase, and then little islands or droplets of that phase, right? Because I can do the tie line thing. So the point of having this phase diagram is you've got a micrograph, and you've got little domains in it, and then you have this phase diagram, and you know the temperature that it cooked at. Then you say what's the composition of the two phases, right? And you can pick that out because at that temperature, you have that phase and equivalent of that one. So one of them is going to be 90% Al2O3, and the other one's going to be like 8%. Let's see, 8% of the other component in this. Not sure exactly what's going on here, but right. So basically, you have those two phases. So that's how that works. In this case, the solid solutions, you have like a crystal of this alumina, right? And then it's the same, like say the alumina crystal is like HCP or something, right? So it's the same crystal structure all the way across. And as you add more alumina to it, like the lattice spacing changes a little bit, but it's the same phase, right? So this is a solid solution. Like the alumina is randomly arranged in the crystal of whatever it is. I'm not sure if it's a vanadium thing or what, but basically in the other phase. So the two things are just mixed, like copper and silver, right? So they would mix an FCC, then they could just, if they're in a solid solution, they're just randomly mixed. You can't tell which one's where. So, and in this case, as you cool it down, then it forms like two phases. It forms two other crystal phases. So if solid solution goes to two crystal phases at the critical point. So, and this could also be like sugar and water. When you cool it down, it makes sugar with a little bit of water in it, and water with a little bit of sugar in it. Right? As you cool it down, you're going to get more and more water as you cool more and more sugar in the sugar. So water depletes as you get to a colder temperature in the sugar crystals. Right, so it will be the same kind of phase diagram. So anyway, so that's with a single, that's kind of a single, or it can be liquid. Anyway, so it can be a lot of things, basically. But this is showing for two polymers. Right? So for two polymers, let's see, I think this is two polymers. This is two polymers. So it's a mixture of two polymers. One has a different molecular weight than the other. That's why it's shifted over to the right. Right. And it's showing that this same phase diagram. But so one of the polymers can crystallize. So it's got this crystalline melting point is depressed by adding an impurity into it. So you see the melting point drop. So below that line, it crystallizes. And then up here, it's a mixture of the two polymers amorphous. And then if you go into this region, you get a spinol decomposition, like a web structure. And it's going to make compositions along the tie line, like in that composition or this composition. Right. So it'll phase separate into those two. If you're in the binodal region, then it's going to make nucleation domains. So it's going to nucleate phases at spots where there's dirt. So we'll make little spheres, right? Kind of polydispersed spheres. And if you go over here and you quench it down here, it first forms those little spheres, and then it's going to make spheres by shifting over to that and that phase, right? So as you decompose it, it's going to change composition of the two phases. At some point, the left-hand phase is going to crystallize when it goes below the crystallization temperature. So you have one phase that's rich in this component that's going to crystallize when you cool down. So when you get down here, you have little crystal domains inside a sea of almost pure the other polymer, right? And if you're at that point, the majority of the thing, actually it'll be a sea of crystals with domains of the liquid of the other guy, because the majority of the thing's going to be the crystal and the minority is going to be the liquid droplets in a crystal. Right. Depending on how fast you go through this, you can get different structures too. So the thing about phase diagrams is how you use them. Like you're going to use it to compare to a micrograph and figure out what you have from this kind of thinking about this phase diagram and how the history that went through to get to what you end up with. In C case, it just crystallized. You're still in single phase, you just crystallize, make crystals, and that's it. And end with crystals. The whole thing crystallizes. So it makes whatever that crystal is. So polymers, it's always like liquid phase separation. You might have crystallization superimposed on it. In metals, this is all crystalline phases, right? So it's not the same. It looks like the same phase diagram. It's the same Hildebrand equation we're using, but it's like different outcome of it. So we'll talk about that in the next sections about phase diagrams. But then there's this solubility parameter. That's unfortunate that menu thing is here. Huh? So anyway, so Hildebrand came up with this idea of solubility parameter, which is a single number. Okay, and he calculated it by talking about the cohesive energy density, which is basically the vaporization enthalpy for the material, right? So the cohesive energy density divided by the volume gives us what he called the del parameter, or the solubility parameter. And you could tabulate that del parameter for anything, like any material. And from that, so enthalpy minus RT over the molar volume is one way to calculate it. Anyway, you can calculate that for any material, and two materials that have close Hildebrand parameters mix, like pentane and hexane will mix, with pentane won't mix with hydroxymethyl methacrylate or something, or nylon. Right, but if you want to find a solvent for nylon, you find something that has a 13.7 Hildebrand parameter like ethanol. So maybe ethanol would dissolve nylon. Right, so basically use this number, comparing two of them tells you the solubility. And Hildebrand figured out that you could calculate this kind of Hildebrand coefficient from these things by taking, so this thing's the square root of the energy. You subtract the two, square it, and that'll just be the magnitude of the separation squared. And that gives you basically the Hildebrand interaction parameter. Right? Divided by KT gives you that. So this is like a method you'll see people. There's a lot of papers where they talk about using the solubility parameter. Then in 1967, this guy Hansen did a PhD, and he said he could improve on that. So he improved on it by saying it's not just one number. Things have different features to them. So it's like dispersion, so London forces, dipolar interactions, and hydrogen bonds. The dispersion forces are that if you have a material that's got a lot of electrons, and then another atom molecule with a lot of electrons pulls up, the electrons are randomly, like, they aren't just sitting in one part of the molecule, they're like moving to different parts, right? So basically, at any given instant, a molecule that's nonpolar has a slight polarity to it because the electrons are crowded over on one side because they're moving around with KT. So basically, every molecule is going to have a plus minus to it, even if it's nonpolar. So two molecules that come to, if you have two of them that are plus and minus, they'll attract each other. Right, and so the distance between them gets shorter, and this polar interaction is 1 over r squared, or 1 over r. So basically, the attractions, even though it's random, it'll either be attraction or repulsion. The attractions add up more because the distance is shorter. So if you add the same energy for different distances, it becomes a smaller energy. It becomes a larger energy for the closer ones. So basically, you end up with an attractive interaction between things that aren't polar. because of this kind of random positioning of the electrons. That's the van der Waals dispersion force, right? So, anyway, so you have to add that in. That turns out to be like a major component to how things act. Like when you make a crystal or something, that's how this is a component. Some have actual dipole moments, and some have this hydrogen bonding. Hansen just figured you could make up one number from each of those. And so instead of a table, just the Hildebrand parameter, he had like 3: dipole, polarity, hydrogen bonding. And then the total would be the square of that plus the square of that plus the square of that. Square root gives you the total one, which is the same, ends up being like the same, used the same as a Hildebrand. Right, so anyway, this turns out Hansen has like a web page and a software and everything where you can calculate what things will mix. Anyway, so that this is kind of like thermodynamics and like a engineering like approach type thing. It isn't exactly grounded that much, but people use this del parameter a lot. You'll see it in papers. But then there's this issue, like I showed, so you have this asymmetry, like this isn't a symmetric phase diagram, so it's not going to work with this equation because this equation is symmetric. So you can fix that with polymers by doing the Flory-Huggins, like use volume fraction instead of mole fraction, and that'll give you a shifted phase diagram. Or you can, in a general sense, use these Margulis approach. So basically, the simple equation you had, which is XA, XB times A12, becomes like a multi-coefficient thing. So you have A21, A12, and then this is an asymmetric excess free energy that shifts the phase diagram so it becomes skewed. And then you can, the Redlich-Keister approach is to have an infinite number of these, like in other words, you can sum up as many coefficients as you want to make it as skewed as you want. So it becomes almost like a polynomial fitting of the excess free energy. And then so there's any number of these more complications to the Hildebrand, but everything's based on the Hildebrand. These are just to fit a certain curve. Then you need to tweak it a little bit, and then these things are introduced. And again, there's like, I think there's probably 50 equation states, like free energy expressions for mixing for various everything you can think of, right? So it isn't like this ends, like it keeps going on and on. There's a unifac, there's a Prius, there's this and that. So there's like hundreds of them, so. And there's modifications of each of the modifications for various reasons, So, I mean, changes in volume on mixing. This is just the original Margulis multi-parameters just to match up with skewed phase diagrams. Like this is for propanol and water, right? Mixture, and then it's shown like as a skewed because water, they hydrogen bond. So it's not accounting for the fact that they hydrogen bond. So it shifts the curve. So the original Margulis is symmetric, the propanol water isn't. If you do a 2-parameter Margulis, which is this equation, then you can get almost a perfect fit, right? And then there's another equation called the Van Laer. So again, there's like hundreds of these equations. Margulis is the parent one. That's the one that everybody uses. And it works pretty well here with 2 parameters. It matches up for like this simple like propanol water system. It has hydrogen bonding. Then when you plot the activity coefficients for things like that, they're like significantly skewed from what we had before. That's another thing, but I'm not sure how much. We'll probably not deal with that too much. Then let's see. Oh yeah, so this is kind of important. Okay, so the other thing is that so here, I mean, it's strictly a line that you have just the entropy and enthalpy of mixing, right? Or that is here. So you have entropy and enthalpy, right? No matter how you mess with it. So the enthalpy could be like skewed. So it could be say 2-term Margulis coefficient type thing. And this can be volume and number. Basically, you have entropy and you have enthalpy, and that's it. And this entropy part is what's called combinatorial entropy. It means like how the marbles are arranged, and that's it. There's nothing more complicated to it, right? But you can have weird things happen, like when you put oil and water. So in terms of this enthalpic interaction, there's an attractive interaction between oil and water. So they should mix. So you have entropy that favors mixing is always negative, drop in free energy. And this term for water and oil is also negative. So something else is going on with oil and water. Other than enthalpic interaction, it's not a repulsive interaction. Right. So what's going on is that the water, when it approaches the oil, like almost crystallizes on the surface of the oil. So the entropy like drops like crazy. So that's a positive contribution here. That's what makes the water, that's called the hydrophobic effect. All right, and the entropy isn't like how big things are, it's how many. There's a ton of little water atoms, molecules, like arranging around the oil. And also there's the first order of layering and the second order of layering. So water isn't going to act normal when it gets near oil. And because of that, its entropy drops, becomes ordered. And that's the free energy rises because of that. Right. So that's what makes it not mixed. But so this expression won't help that. You need another term that's called non-combinatorial entropy term. So this is pretty common to put that into this equation. So so you have something like, so we start with this, like if we divide by KT, then the entropy term doesn't have temperature in it, even though the sign of it entropic mixing is that it's temperature dependent, but we've removed the temperature here. And then we have just this term here, and this A12, in that case, if you write it this way, is our original A divided by KT. So it's 1 over T dependence to this term. Right. So if you want an entropic term in this, it would have to look like that term, so it doesn't have temperature. You know, the signature of entropy is it's a temperature dependence. We've removed the temperature dependence. Right, so you're going to have another term here that would have to do with like how water organizes when it approaches oil. And then that term actually governs the entire phase diagram for water oil. I mean, it doesn't mix. This term is way too big for anything else because there's so many water molecules. It's just number. It's just like the number entropy. So anyway, so if that's true, like if you have an expression like that, so this is semi-empirical, but basically there is an argument for why that would exist. Like you have ordering on mixing, but you didn't expect from the combinatorial thing. Well, then you can say, well, then I can make my Margulis coefficient go to 0, and then I can find a magic temperature where it's called an athermal mixing. Or it's an ideal mixing. Or it's just following the ideal mixing law or X ln X thing, the comfortable equation. Right. So all right, so that magic temperature is this T star thing. So if you say A12 equals 0, then you find out that B is minus A over KT star in this equation. You plug that in, then you have A, then you can say you have, oops, you can say you have A by KT, and you have B is by KT star. So you have the K and the T, put another T here, you have T by T star. And then this expression becomes the original Hildebrand term, 10 to 1 minus T over T star. Right? And T star is a critical temperature where you reach ideal condition, ideal mixing. It hasn't phase separated. It's not a phase separation point, but it's where you get athermal. There's no temperature dependence anymore. We've washed it out. This non-combinatorial entropy perfectly matches the enthalpic interaction that would have driven mixing, would have driven demixing. Right? So they match up, and that thing ends up being the point where that happens. Right. So anyway, so the reason to show you this is because this is the same function that we had when we looked at in chapter or whatever, single component system. We ended up with the same function governing Landau phase behavior. Right. So this thing of like this magic temperature becomes like a critical temperature. It becomes like the thing that you talk about for phase, like you can describe the whole phase behavior from this critical temperature. It's like comes from associated with the Landau thing. And then all the transitions, like in the book, this is for the Curie transition, as a Curie somehow magic temperature for whatever. So basically this kind of approach is going to be like, you'll see this function like 1 minus T over T tau or T star over and over again. And that's like a critical temperature where the non-combinatorial entropy matches the enthalpic mixing term. So this thing you should become happy with too, like the long term. This idea that you have a 1 over t minus t, 1 minus t over t star. Or this can be like, because this would be t over t, so you could have, what does that end up with? T times, anyway, it can be 1 over, it can be written in different ways, right? So basically, this would be like 1 over t, 1 over tau, 1 over t minus 1 over tau. You could do it that way too. You pull the t out here. So anyway, so that expression also should become, you'll see that again that way. Like that expression is important to talk about these behaviors. I mean, I mentioned that you can, so people, so the next thing is just like, you'll see every time, like someone plots free energy and then mole fraction. They say the slope is the chemical potential. But so it's a problem that isn't really true, you know, so you have dgdx doesn't equal dgdn because it would be dgdn, dgdx, dxdn. Dxdn isn't one. Dxdn is this messy thing with all the n's, right? So basically, this is the graphical determination of the chemical potential, and it's used to decide like if two phases are in equilibrium with each other. But basically, it's a lie. You know, it isn't true. Like it isn't true that one of this is one. You know, that doesn't work. So anyway, so basically you have to keep that in mind. It's a simple graphical thing to do. If you have, and it only works, you have mole fraction here. If you're doing volume fraction and Flory-Huggins, they do the same thing, which you'll see people do. You know, it's definitely not true for volume fraction, and it's not really true for mole fraction. Maybe you could work this to think that this thing would almost be one for mole fraction, but basically it isn't, and then it's definitely not for a volume fraction, right? So, but anyway, nonetheless, like we'll continue on as if that's true, because in the next chapter in phase diagrams, this kind of construction is one of the main ways to tell what's going on in more complicated systems. So that's just a note there. I already went through this, like the relation, how you relate the activity coefficient to the Hildebrand term, right, through those two equations. I obtained that in the Gibbs dual I went through last time. So that's it for the solutions. Any question on that stuff? I mean, it's a lot of stuff, but I need to finish to go through that. This week's going to be about, let's see if I can get this guy. It's like the homework this week is, it's also a borrow. I've been like busy with this other class, I think, so just using the old homework so far. Like I've used one new one, but anyway, this is about batteries, and it ends up with a phase diagram, this eutectic phase diagram. So that's like one of this phase diagram is the thing you need to be like kind of familiar with for, and they talk about like taking traces through this phase diagram and getting what the micrograph would look like from the phase diagram. If your materials, like you did this already. You know, if you aren't materials, this is kind of like one of the core things that people do. All right, so this paper is about battery electrodes, but it's using that phase diagram thing. So that's what the next section's about. You know, it's just and this again, like the eutectic. This is the eutectic phase diagram, so it's kind of the bread and butter phase diagram for materials, I guess. One everybody cares about. So the eutectic point's this point here. So this is a mixture of silver and copper. They both have the same crystallographic structure, FCC. So you have simple cubic would be the corner ones, and you put one on the face. Then every face has the same one. So that's an FCC. That ends up having the same density as HCP, hexagonal closest packed. So you have within the structure, there's a hexagonal plane, the 111 plane. It's the same plane as a HCP, which would be like your classic cannonball plane. You have one in the middle and then 5 cannonballs around the other one. Looks like a hexagram thing, right? So because that's your standard shape of marbles, that's what it forms. It turns out like if you go, if the layers, so there's a way to shift the layers, you can have 3 different ways that the next layer of hexagonal things would be. So if it goes like A, B, A, if it goes A, B, A, if it repeats, then it's FCC, and if it goes A, B, C, it's HCP. So ABC would be another twist to it. All right, so it was the closest you could pack balls. Right, so the idea is that these silver atoms and copper atoms are basically just balls, right? And the difference between them is that one of them is 4 angstrom and the other one's 3.5 angstrom. So there's a slight difference in the size of the two balls. But so if you imagine you had marbles and one was like 1, and the other one was 0.9. Well, you could put in some of the marbles, they would mix, and you would still make a hexagonal structure if you shook it, right? Up to a point, like when you get to 50-50, 0.9 and 1, then it would separate into two different crystals. That's the point of this phase diagram, right? So to heat it up enough, it goes into a liquid, and they mix. You just have a liquid silver and copper mixed together, and then you cool it down. And if you're near the silver end of it, you have this 4.1 angstrom spaced FCC structure. So the A would be the distance between the corners here. And so it's 4.1 angstrom for silver. If it's a copper FCC, it's 3.6. And so anyway, so you make silver, and you can accept quite a bit of copper, up to like something like 16% copper. It's still a silver crystal. It still has a 4.1. And so that crystal's got some kind of extra space in it, putting a smaller thing into it. Oops. So, right, so that's what's going on like in this region. Like you start with pure silver FCC, and then it's still FCC all the way up to 18 or 16%. Right. And then all of a sudden, well, the copper decides it's incompatible, like it isn't the right size. So the copper decides it's going to separate out, and it's going to make almost pure copper FCC. Same crystal form, but a different lattice spacing. Right. So it's gonna, once you get over to here, well, you're gonna make like a little bit of copper in a sea of silver. Right. And the further you go over, you're gonna get more and more copper until you get to like halfway between the copper line and the silver line. And that's where it's going to transition to a copper sea with a little bit of silver islands in it. Right. So the tie line between these two, like if you were here at P, and that's almost pure copper with this little bit, like maybe 10% silver FCC crystals in it. And so use a tie line to say what the micrograph is going to look like. Like you take a look at the micrograph, you have little dots in it. It's about 10%. You know you're at that temperature, and then you can actually get the composition of the dots with inside the microscope. You know, use EDEX and get the composition, like how much silver, how much copper. You get the composition of the other one. So just with the microscope, you can map this out. And you can get the composition of the two parts. You can say that those are in equilibrium, depending on how you quenched it, right? So that would be like a rapid quench down to P. Right? So if you go over here, so as you put in more copper, so that's when you have the two crystals in equilibrium. If you're up here, then the silver crystal is in equilibrium with the liquid. Right? So you have silver crystal, and then you reach too much copper, and it's acting like a diluent. So it's, as you add salt into ice, it melts it. As you're adding copper into silver and it melts it, it reaches a point where it can't handle that much copper, and it melts into a liquid. And at that point, you're going to have some silver, you're going to have some liquid in the silver crystal, like droplets of liquid in the silver crystal. As you go over, eventually you get silver crystal in the liquid phase. Like when you're halfway between those two lines, you have silver crystals floating around in liquid. Then finally, it just all turns into liquid. Like you add too much copper and you melted the silver. So this is like adding salt to ice. You're melting it. And the same happens with the copper. You add in silver, it melts it until you get to pure liquid silver copper. Right? It's got whatever composition you put in. So if you put in a composition here, it splits into two. It's going to be like 90% liquid, 10% copper crystal with a little bit of silver in it. Right. So you can kind of use these, when you're using this to say at equilibrium at that temperature, what would it do? But in fact, when you quench it down from liquid to crystal, it locks it in. Like it's not going to, the atoms can't move, right? They're stuck. So you have to somehow figure out figure out how, like what, what it actually would form in those conditions. And the other thing that's weird is if you come, all right, so there's a point, so it's the lowest point where it would form a solid. It's like form some solid here, some solid here, but still some liquid. Then finally, you just have a transition from liquid to the two solid phases. So when you get to this point, it's gonna go from liquid directly into pure silver and pure copper crystal. Right, so this is the eutectic point. So you have three phases in equilibrium. You have the silver crystal FCC, copper crystal FCC, this liquid phase. It's a mixture of like 45% copper and silver. Right, so it's kind of a magic point. It's the lowest point. It's the lowest crystallization temperature. If you have that composition, it's the earliest for turn to a full liquid. So it's a little bit of a magic point. So anyway, so it's complicated. It can get a lot more complicated than this. But basically, this is the parent of the complicated phase diagrams. Now that you want to think about. So the key points of this are that you have like tie lines. You can get compositions from. The composition of two phases are at the ends of the tie line, and the amount of the two phases, which is equally important because you're looking at a micrograph and you want to say, what are the drops in the sea? Which is the sea and which is the drops? So the equilibrium phases won't tell you that, but the tie line will. So if you say in here, then the sea is this, is the silver and the drops are the copper. Right, so you have to kind of get a feel for that. Should be able to calculate. So from a micrograph, you can calculate what percent, and this will tell you what percent. And then basically they should agree, and the composition should agree, and then you know you're mapping out that phase diagram. So they can get, the phase diagrams can get a lot more complicated than this, but basically this is the first of the complications, I guess we'd say. This eutectic phase diagram. Anyway, so yeah.
What is the difference when we are slow cooling or relatively cooling in the eutectic region, like 0.45 or something?
Yeah.
In that point, if we rapid cooling or like cool rapidly or slowly, what is the difference between that?
Well, if you cool slowly, basically people look at like a rapid quench here, and then you end up with stuff like here. Stuff like this. So you get, it's almost like the spinodal decomposition, like you end up with something like a web, So see some kind of colorful structure like a tiger stripes and things. Then that's a rapid quench into eutectic. If you go slowly into it, if you go slowly enough and you just hang out at the eutectic temperature, you're going to just get like mostly silver with islands of copper. Like you won't get that structure because that structure is kinetic. It's like a kinetically derived structure. So this is actually decorating the fluctuations. Like in other words, you're in the liquid and you got copper and silver, and they're clustering a little bit, like this copper together somewhere and silver together, and then they break apart. Those time-wise is doing that all the time. That makes like something that looks like this tiger stripe. So if you quench down, it just augments that and locks it in. It turns a crystal, right? So it locks in the fluctuations. What you're looking at are the fluctuations. So basically, if you cool slowly, you won't. Those fluctuations will relax and it'll just form domains. So it's kind of a kinetic feature that you get this.
So we'll get amorphous.
No, the only amorphous is liquid in this. There's no amorphous.
If we slow cool, cool it slowly, then we'll get still crystal.
All crystal. The only thing you get is crystal out of this. To get amorphous, you have to put the metal into a bullet and shoot it against a cold wall. Then you can get amorphous metal. So you have to really go way out of your way to get amorphous metal. It's possible to do it. People do it. Basically, it's not going to happen if you're just piddling around.
So it still goes to the solid region from the liquid region.
Yeah.
If we pull it rapidly or slowly, but
yeah,
the structure is
right. It'll lock in something like that, some tiger stripe thing, which is a reflection of like what the fluctuations were that it came from. And it just grows on the fluctuations, and it isn't time, it's a matter of diffusion, right? So it's a kinetics issue. So it's like thermodynamics is guiding it, so you can tell what the composition of each of these phases are, but the structure is determined by kinetics. So this whole thing with the phase diagram is really a combination of thermodynamics and kinetics. Thermodynamics tells you like what it should be if you had forever to get there. And then the actual thing that comes out will be different. And it's going to depend on the cooling rate that you go through for it. So
And if have more fraction like 0.8 or or less 0.2, then we need like skip the part like liquid plus solid. This part if we cool it rapidly.
that's when it gets, oh, if you cool it rapidly, yeah, you can quench down. It's called a quench, and you quench to here and you get those two.
So we skip the middle.
You skip by going fast, basically by called quenching. So you take the metal and throw it into a bucket of water. You quench it, right? And then you get that. But if you cool it down slowly, it becomes a little bit more interesting. Like, I mean, not maybe it's not what you want, but basically it's kind of interesting. Like you're going to come down here, then you're going to separate into those two phases, right? So initially it's got mostly liquid and then islands of this copper in it. And as you go down, as you cool down, so the copper becomes the major phase when this thing reaches halfway. So then at that point, you have a copper with liquid islands in it, right? And the liquid composition will go down until it reaches a eutectic point. So in other words, you can pull this line down, 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 and finally liquid will form a eutectic. Then it's going to form, if it's going slow, it'll form silver with copper, silver phase, another phase in it. So it's not a liquid phase, it becomes a silver phase. The liquid phase turns to silver with some copper in it. As you cool more of that phase becomes more silver rich and less copper rich, while this one's becoming more copper rich and less silver rich. So the eutectic kind of governs when you transition from liquid to the other phase as you're doing a slow cool. So you can see, like, depending on the rate, you can get a lot of different structures in the same composition at the same temperature. It's pretty much wide open. So figuring that out is the game of these diagrams. That's what you in for. And mostly doing it. Well, you do crystallography, so you can get the percent of the two crystals and what crystal phases are there. Then you do a lot of TEM of metals, you know, to get the crystal. You can do crystalline diffraction and TEM, so you can diffract actually within the little domains. You can also do EDEX and get the composition of the domains. So you can put that all together, and people that do this are like people that make jet engine turbines, turbine blades, titanium, super alloys and stuff. So they'll spend their whole career just doing this, you know. We had like 2 people that did that here, and one left, went to Texas. The other guy went to Oklahoma because GE Aircraft is in town. So there's a lot of turbine blade, and from them, there's like a bunch of companies that do like the turbine engines. They pull them out of the jets, and then they have to take, and then each of the blades is a single crystal, single titanium superalloy crystal, and they're like this big, you know, and they're spinning around. I don't know how many thousands of hertz or something, you know. So if one of them breaks, it kills everyone on the plane. So they have to make sure that there's no flaws in them, and they're so expensive that they reprocess and coat them. So there's companies that just do reprocessing and coating of turbine blades for jet engines, you know. And then there's the GE is manufacturing them. So there's a lot of work for that in Cincinnati. But and then the Wright-Patterson Air Force for the military ones. It's like right up the road in Dayton. So, but anyway, I think at this point, well, there's this metallurgist, but there's nobody doing that work, I think, now. That was really David was doing it. He was like the expert in that area. But anyway, so who knows, somebody might come along to do it. But anyway, right now it's not as much. Anyway, they would spend like all their time in a TEM, just looking at these phase diagrams. And I'll show you, it becomes a lot more complicated than this, right? The other thing is, like you're saying, amorphous, and that's for polymers, it's like all about the amorphous. So you lock in like a PET water bottles would be crystalline at equilibrium. So it would just be like a white powder. So because you can quench it so fast, because the kinetics are so slow, so the kinetics here are like nanoseconds, and in a polymer, the kinetics are like seconds to minutes. So there's like maybe 10,000 times difference in speed. So it's possible to like quench into glass state almost always in a polymer. Right? Whereas in metals, it's not possible to do that unless you, like I said, they literally take a gun and shoot it against a wall to make amorphous metal. And it's useful for some things, but it was also a research topic, but it kind of died out, I think. So anyway, this programs to, have you guys used these things like CalFed already, or you have? Good, you have? Yeah, all right. So anyway, this CalFed doesn't work on a Mac. This ThermoCalc works on a Mac. So I use ThermoCalc because it's a Mac, but basically CalFed's a standard thing. This is a solder phase diagram, just like a eutectic that you can calculate from it. And we'll show you, like, I'll go through like how these things are calculated. And basically it's going to be based on the Hildebrand equation, believe it or not. I mean, it doesn't look like it has anything to do with it. Basically, all this stuff can be obtained through basically the Hildebrand equation and then kind of slight modifications to it, which seems really strange at first, that could be true. I went through that. This is saying that thing about cooling, the same thing that I just said, this is a polymer phase diagram that I already went through, right? The idea you can have crystallization, basically the liquid-liquid phase separation on it. And all right, so this is this business. So you say you want this as a solid solution phase diagram. So you have a liquid of two metals. This is germanium and silicon, and it's pretty hot, so like they don't melt at room temperature. Right, so you have both of them have this diamond cubic structure, which is I think it's kind of like two FCC structures inside of each other, more or less. You go out like a quarter. So you have an FCC structure, and then you go out a quarter distance and put an atom there. You do that for every atom, and then you end up with this diamond cubic. So diamond has that structure. Then all the semiconductors have it, basically germanium, silicon, and some other materials have that structure. But anyway, so these two have the same structure. So it's similar to the copper silver, like they can fit in each other's lattices, more or less, right? So anyway, so you're going to have like a liquid phase and then the solid solution phase where they both form diamond cubic across the entire spectrum from 0 to 1. There's no breakup of this thing, right? So if you look at so these are the two so you have the solution phase has a Hildebrand function, which looks kind of symmetric, like this is free energy plotted on a Hildebrand function for a given temperature. Again, like as you go through the temperatures, you go through the different temperatures, that curve changes and eventually reaches like multi-phase equilibria, right? So this is for at T3, the solution part Hildebrand and the liquid Hildebrand. Right, so if you're at some composition, or this is the solid solution is like the co-crystal. This is a crystalline phase, and this is the liquid phase. This is the diamond cubic, and that's the liquid. So basically, if you're at this temperature T3, and then you're at 20% germanium, because the lower curve is the solid solution, the crystal phase, that's going to form a diamond cubic crystal. If you're at 80% germanium, it's going to form a liquid because that's a lower the two free energies. So you plot the two Hildebrands on top of each other. The one with the lower free energy is the one that wins. Like you want to have the lowest free energy. If it was solid, it would form liquid because it would lower the free energy. And so that the lower one wins. And then if you're at a point where the line crosses, again, this isn't really the chemical potential, but this is how it's done, So basically, it intercepts both of them, right? So that would be the phase, those would be the phase compositions of these 2 points where the liquid and the solid are in equilibrium with each other. If you fall at a composition in between those two, it separates into these two phases that have the same chemical potential, right? It splits it up, and that's the tie line. As the T3 is this plot that gives you those two things. And so by changing the temperature, you change these curves, and then you can map out this whole phase diagram, right? Like T1. So the only thing that's comfortable at T1 is the liquid. So at T1, it's all liquid. Right? And then T2, when you're at the pure silicon part of it, then that's where the two liquid and solid are the same. So T2, there's only one point where they cross. And then T3 is the one I showed where you have equilibrium between the two. So part of it, the solid is stable, and the other part, the liquid, is stable because it's got a lower free energy. And T4, so the relationship between the two curves is shifting, right? That's the point. And then T4 is where you also have two equilibrium phases. You could draw a line here, so that one and that one, which correspond to that point. And T5, there's only one point which is over at the pure germanium. Right, so you can, so just using this Hildebrand equation, you can make out this phase diagram. Even though it looks like it has nothing to do with these. Right, so it's kind of funny how it works out. Basically, you can work this out for any phase diagram. You can do this kind of thing, and you can have more than two phases. You have more than two circles, more than two curves here. So then you can start to figure out all the phases that could be at equilibrium with each other. So we had this thing. So we figured out in the homework last time, it was like take this equation, get that equation, and that gives you the activity, log of the activity. Integral of that gives you log of P, which is that log of the activity. So you can get this chemical potential equation. So that'd be the chemical potential for, like, the germanium, say. So the chemical potential is going to be of the phase of the component. So it's like two things to every component. Like, so the chemical potential of the germanium in the diamond cubic phase, and then the chemical potential of the germanium in the liquid phase, and the chemical potential of the silicon in the diamond cubic phase, chemical potential of the silicon in the liquid phase. So there's four chemical potentials, right? When you have binary mixture, two phases, 2 times 2 is 4. So you have 4 chemical potentials here that equal each other for the two phases. So it's a germanium chemical potential in the diamond cubic equals the chemical potential of germanium in the liquid, and the silicon chemical potential in diamond cubic equals the chemical potential of silicon in the liquid. But the silicon chemical potential in the liquid doesn't equal the germanium chemical potential in the liquid. Right, so it's the thing itself in two different phases are equal. Anyway, so there's 4 things, 2 equations. Two equations govern the thing, right? So you can write that out like this equation, that equation, then those two have to be equal for that component, for like silicon or germanium. So you have 2 equations, and then so you can start to add up like equations and unknowns. You have the unknowns are, the temperatures, the unknowns are the 2 compositions of the 2 phases, and you have 2 equations, so it's possible to solve it. 2 equations, 2 unknowns, right? And that's kind of how you can write a program like the CalFAD thing, whatever that is. So you can write something like CalFAD by figuring out these chemical potentials using and that'll just plot out the compositions at a given temperature for the thing, right? So, all right, so the route to get to that is to say, so we have that equals that. That means that so when you add 2 things, log of something plus something is log of that times that, right? So if we're dividing here, so it ends up log of the ratio of those, that's going to be the difference in the chemical potential from the solid to liquid, which is the heat of fusion, right? Minus the entropy, temperature times entropy of fusion. Right, so it's heat of fusion you can look up, like you can go to this NIST web book, gives the heat of fusion of everything in the world. Like literally everything in the world, just go to NIST, National Institute of Standards Technology, web book, and it has it on it. Or you can Google it, they'll give it to you too. But the NIST one's probably more reliable place. So it's a national standards lab. It's supposed to be like perfect. All right, so from this you get these, you can rewrite these 2 equations like this, and then this chemical potential is just going to be the heat of fusion and then the entropy of fusion, which the entropy of fusion is related to the heat of fusion at the melting point. So if you know the melting point and the heat of fusion, you can get the entropy of fusion, right? Because at fusion, the two phases, the crystal and the liquid have no free energy difference. That means that we did that before, and then that means the entropy is defined. Entropy, the thing you can't measure, is defined by the temperature and the enthalpy. Right, so then you can just rewrite this thing, and it looks just like the thing we had before. 1 minus T over T star, the critical temperature that we had before from the Hildebrand, right? So it's T fusion is the critical temperature here. It's 1 minus T over T fusion. So that expression of 1 minus T over T, some magic T, is like governing thing you'll see in thermodynamics like over and over again. So you should remember that expression, just like you remember the X ln X thing. So when you see that expression, you should feel comfortable that it's like a free energy expression, because it's basically swapped out entropy for enthalpy, and you get that expression. And we did that when we did it with the Hildebrand interaction parameter. It was the enthalpy of mixing and the non-combinatorial entropy, and you end up with the same expression. So it's got something to do with going back to the free energy expression. G is delta H minus T delta S. And that just ends up giving you this because of that, because at the transition temperature, the entropy is at that. Right, so anyway, so then we can get delta U just in terms of two parameters, and the two parameters you can get from this web book. It gives like the temperature of melting, and it gives some expression for what the enthalpy of melting is at different temperatures. Like it gives a polynomial thing for it. So basically you can get those two numbers by just Google search, whatever. Right? And then you have what delta mu is. Go and solve the liquid for the two components and the mixture. That means you can get the numbers. You can get everything in this equation. You know the temperature, and you can get it. You get everything on this equation basically, right? From that, just from those two numbers. And then you just plug and play. You say like X liquid, X solid is this and that. So you reduce these equations down to this. So you have a log, so you turn the log into the exponential of the enthalpy expression. And then that gives you the mole fraction liquid is if you know the mole fraction solid, and the mole fraction liquid if you know mole fraction solid. But so those are two equations of four unknowns. Like you don't know XA, right? There's four unknowns here and two equations, but you know that XA liquid plus XB liquid has to equal 1, and XA solid plus XA solid, XB solid has to equal 1. So actually have four equations. So you just write XA solid as XA liquid minus 1 minus XA liquid. And there's two unknowns and two equations. So then you can solve that thing. You can either do it mathematically or numerically. Like just run an iteration until it solves it. And then we have, the program's going to do this numerically because the equation can be expanded a little bit here. But basically this equation you could solve with a calculator. So anyway, so that gives you two compositions at any temperature that you want. Just change the temperature, you get two compositions, and you could map out this phase diagram from that. If you know the melting temperature and the enthalpy of melting, right, for the two components, which were listed in the NIST web book. And so it means you can just calculate a phase diagram, which is CalFed. That's what CalFed's kind of doing. All right, so hopefully that's kind of clear. When I first saw that, I thought it was pretty interesting that you could do that. So I don't know. It's kind of neat how you can just take. You wouldn't think that thermodynamics could predict that, put it that way, from the melting temperature and the enthalpy of melting. But it turns out it's there. Like it's within it, as long as you're keeping track of like number of equations, number of knowns. So that doesn't include some things, right? Like in other words, when you change the temperature, there's a heat capacity change. In other words, the heat capacity, so if you integrate the heat capacity times delta T, that's another energy term. Like it takes energy to heat something up, put it that way. So this is just including the transition enthalpy, not the enthalpy of taking it from one temperature to another temperature. And this enthalpy of fusion is at the fusion temperature. So if you did it at a different temperature, so you're at some temperature T, you have to take your material up to the fusion temperature to use this, and then take it back down after. You take it up to the fusion temperature and make a liquid, the heat capacity of the solid, and use heat capacity of the liquid to bring it back down to the temperature where you are. So you need to add into this a heat capacity term. That's an integral Cp delta T, two of those, one for the liquid, one for the solid. Right, because wherever you are, it's either going to be liquid or solid phase. You need to integrate to get to the melting, unless you're exactly at the melting. Right? So anyway, so that's why in these these are from the book. So basically, there's one delta Cp 0, the black lines, and then you include that integral, and you get kind of a better match somewhat. It's actually worse in some cases, but so the delta Cp is included and not included. The black lines are the experimental for the delta G, and the dashed lines of the calculated with no CP. So it's simple, like this is a simple thing to look at, and then it can become more complicated and make it work right. This is just showing how this works. Like you just integrate for the solid and integrate for the liquid, Cp dt, and then you can get the transition to the temperature you want. Anyway, so that's the simplest of the phase diagrams, is solid solution one. So there's more. This is what we're looking at. So solid solution. So you have the two things co-crystallize all the way across, and they form a liquid state. Right? So you have a transition liquid to solid. It goes through the solid liquid region because of the Gibbs phase rule. And then you can have this kind of phase diagram, which has this congruent melting, means the liquid melts into the same composition as the solid. So here, as you take the liquid down, it's gonna crystallize into a solid that's a different composition than the liquid. Right? So the solid precipitates out of the liquid until you finally reach pure solid, and it precipitates out. As you cool this down, it's precipitating different composition solids. So you're not going to get a single composition solid out of this. You start with, if you cooled here, you'd start with that composition solid. As you cool down, by this point, you have that composition solid, and you have everything between those two for the solid that precipitated out of the liquid. Right. So if you have congruent melting, you have the liquid composition at that congruent melting point, you form a solid that's exactly the same composition. So that's the only case where you do that. You form a single solid that's exactly the same composition as the liquid. Right. This is for salts, sodium chloride and potassium chloride. So there's reasons that you get phase diagrams like that. Then the eutectic that I said before. So you're going to cool down, you're going to form two solids, two different solids. L goes to AI, alpha plus beta. If you took chemical engineering, then you have this other set of phase diagrams, which look almost the same, and it's worth pointing out that they're almost the same, right? So you have, this is a single phase, like liquid gas, liquid vapor equilibrium. Looks just like the solid solution. And then this is called the azeotrope. We have like alcohol and water, and you try to distill it going across this, you can get to the azeotrope. You can't get more alcohol in, no matter what you do, unless you put in a third component or do something else. It's an azeotrope is like it's a stuck point in a distillation process, like where you can't purify the stuff anymore. It comes up when you're trying to make grain alcohol. So, and there's like a positive and negative deviation in azeotropes. And this is the solid solution. This is the congruent melting. It's like the same phase diagram, except in this case it's liquid to crystal. This is kind of like liquid to vapor. Right? And then there's a thing called a heteroazeotrope, which you'll never see, which is like the standard bearer for metal. So this azeotrope is like the standard bearer for chemical engineering, processing, and eutectic is a standard bearer for metals. Like this is the thing you would have to memorize in chemical engineering class. This is the thing you have to memorize here, eutectic. So it's kind of funny. The congruent melting is an oddball, like it's some salts mixing. And then this is the standard. And then this thing is a real oddball. And then this is the standard. Right? And then these two are both kind of the simple simple situation, it doesn't really happen that much, right? So anyway, the phase diagram, so you see like phase diagram, you think like, whoa, that looks exactly like the same. Well, it is kind of the same thing, and it's kind of different, you know, so it's vapor liquid, this is solid liquid. But they end up, the basis of the things are the same, like we're kind of using the same structure to get to this. So I think that's, let's see, I think we're out of time, but anyway, I'll start showing like where this came from, the congruent melting. And then eutectic. I can go through those two next time and then do the homework. I think that's kind of what you need to do the homework with. The rest of this, there's more stuff about how you calculate it. So that you don't need that necessarily for the homework. Oh, you need this for the homework. I'll go through this too. Intermediate phases, but right. So we quit there. I guess let's hopefully get any questions or anything. But stuff. So, right.